So we're going to be presenting about characterization techniques at the nanoscale. And I'm Sarah, and this is
Amit.
So to start out, just a little history on microscopy techniques. So microscopy has been around for a very long time, since about the early 1600s, when people started using the idea of light microscopy to look at biological samples. And this was a very important technique at the time because it helped us really to understand the human body and how our body works. And one of the actual very first discoveries was looking at red blood cells under a microscope, which changed the idea of blood altogether. So as time went on, we discovered that we needed higher resolutions and the ability to see more things because we are limited by the wavelength of light, which the wavelength of light is on a scale of hundreds of nanometers. So you can't get down to that nanometer level using just light alone. And this image here is just a comparison of what you can see as far as the eye, which we see up to about the millimeter range, and then the light microscope versus the current technology of electron microscopy and beyond. So to start off, we're going to talk about some of the electron microscopy techniques. One of the first ones is the scanning electron microscope. And this microscope uses beams of electrons rather than light, as was previously used in the original microscopes. So they use this electron beam, and it's focused through different magnetic lenses down to the sample, your specimen on the stage. So it's going to interact, do a little tapping mode or other types of mode, depending on the specific type, to come up with the topography of the sample. So it's a 4, yes. So on a macro scale, it's generally the same idea, where you have this probe that you actually use to feel around the surface of the sample, similar to, say, someone who's blind and they have their walking stick with them, that they kind of tap around and feel the area. Rather than actually seeing it or using any kind of beam or light, you're using this almost touching method. So one type of scanning probe microscope is the atomic force microscope, which uses this cantilevered beam. Now this beam has a very sharp point on the tip that actually interacts with the sample. And it will run across the surface and measure the deflections, or the different heights on the sample. So these deflections are measured by taking a laser beam and reflecting it off of the top of the cantilever beam, which is then projected onto a position detector. And depending on the deflection of the cantilever beam, it will be projected on this detector, and that will convert into determining where the point is and how far off the surface it is, and that will eventually translate into a topographical image of your sample. And these are just some examples of AFM images. This is also very useful for, say, biological samples because it doesn't need to be conductive, and you can use it for just about anything.
Thanks. So another kind of probe technique is a scanning tunneling microscopy. So it is similar to AFM, we can say. It's kind of probe technique, but there is a little bit difference. So what in 1981, the IBM employees like Rohrer and they discovered this technique, and they got the Nobel Prize for this one. And it is more than a pointed electrode. So in the AFM we have the tip. Here it is electrode. So electrode is the one which conducts the electricity for us, you can say, electric current. So over here, this tip is kind of tiny nanoscopic electrode, and here we have the sample. Over here, there is one piezoelectric material. So these are kinds of material are the ones, if you put something on that material, like even it is a nanoscale material, it vibrates at a certain frequency. So what is going to happen? And over between the tip, if you in this microscopic picture, you see there is one kind of tunnel in between the electrode. This is red electrode and the surface. So it the current current transfers through that tunnel, and this piezoelectric material is going to vibrate like that, like that. So it won't make sound like this, but it does, something like that. So based on that, you get the image, the current that passes. Well, this is also one of the like revolution, you can say. With STM, people could manipulate the atoms, individual atoms. So over here in this picture, you can see people have this Eagler from the IBM. They have manipulated the iron atoms on a copper surface, and they have arranged in a like circular way. Another technique is X-ray diffraction. You can call it as X-ray scattering as well. So in this one, Wilhelm Röntgen, he discovered the X-rays. Well, he named it as X-rays because he saw that some photocathode is giving out some kind of rays. He was not sure, so he gave that some unknown name, X-rays. So he got Nobel Prize for that. After the discovery of X-rays, there was kind of revolution in again the techniques that can these X-rays can be used for, and so people started doing research on it. And these two father and son, William Henry and William Lawrence Bragg, they discovered X-ray diffraction technique. Well, this X-ray diffraction, you can use it for microscopic level, and small angle X-ray scattering, you can use it up to nanometer scale. I'll just give you the demo of once I'm finished with this presentation kind of thing. So the principle is, can you pass the I'll give you the demo here itself. So suppose this is the tip of my pen is a nanometer scale particle, or maybe nanotube you can say, and this pointer, consider it as X-ray. So you can see when there is nothing, it's just a one pointer, but light is going to scatter a little bit. You can see that. And based on the angle at which I rotate my light, say that X-ray, it is going to give me the different diffraction pattern. So that theta is the angle at which I am rotating my X-ray. So based on that, you can get your size, like the dimensions of this crystal, or maybe say defects in the material. Well, this is typical setup of XRD experiment. This is called as a goniometer. Here you put the sample, again you put the incident beam. Well, sometimes instead of rotating my X-ray here, you can rotate the sample here itself, like in different angle. That angle is calculated based on that formula that in this previous slide, 2d sin theta is equal to n lambda, where lambda is the wavelength of the X-ray. You can get the signals at particular angles. Based on that, you can find out the defects and whatever you want to know. So what kind of information you can get? Spacing between the atomic layers, crystal structure. Well, and one of the big revolution, like in with the help of XRD, is the finding of the structure of DNA. Watson and Crick, they defined the model of DNA. Then a lot of people did the research on it. A lot of controversies involved again, involving Rosalind Franklin. She was another researcher who did the research on DNA with X-ray crystallography. So these are the things that you can do with XRD. Just to summarize what techniques we have discussed, TEM, well, this is the scale to nanometer level, 50 nanometer, 100 nanometer. So these techniques, this is the range. This slide gives you the range in which you can carry out the experiment. So for TEM, you can go up to 1 nanometer to 100 nanometer, more than that. Same for scanning electron microscopy, you can go from 50 nanometer onwards. X-ray, single crystal X-ray crystallography or something, you can get up to 0 nanometer to 100 nanometer. AFM is there. So these are the techniques that we can use for characterization. Thanks.